right, let's take a look at this example for power. So whenever I'm dealing with average power, remember I can find work one of three ways. I can either use a force times displacement, an area under a force position graph, or I can use the work kinetic energy theorem. So let's go ahead and set up our question. A Chicago marathon runner with a mass of 50 kilograms runs up the stairs to the top of the Willis Tower, the tallest building in Chicago, 443 meters, in 15 minutes. Ooh, minutes. We'll probably have to convert that to seconds. What is her average power output in watts and in horsepower? Okay, so I have someone running from the bottom of Willis Tower up all those flights of stairs to the top. So they are starting at one point, ending at another point. That's kind of my clue that I'm going to use the work kinetic energy theorem. Also, that's my clue that it's going to be an average power because it's taking place over a period of time. So let's set up our work kinetic energy theorem, see what crosses out. We're going to assume no friction. We're going to assume she's not like dragging her arm up the wall the whole way. We're going to assume she starts and ends stop. She starts the race. She gets to the top. Woo! She stopped. However, she does have gravitational potential energy when she gets to the top. She did not at the bottom. And there's no like spring system working in this case either. So next, we want to find that work in. So that work in is going to be equal to UG2. So the work she does is equal to mass times gravity times height. All of the work she did went into gravitational potential energy. So when I talk about her average power being work divided by time, I'm talking about all of that gravitational potential energy she gained divided by the time. All right. So in this case, we will plug in our numbers. So we had 50 times 9.8 times the height, which was 443 meters, all divided by a time of 15 minutes, but I got to get that to seconds. So that'll be 15 minutes times 60 seconds in a minute. Putting that all together, we find she has an average power output of, where did I write that down? There it is, 241 watts. Now, if you remember our climbing Rib Mountain example, remember this is just her output. This isn't necessarily the rate at which her body is burning energy. Okay, so keep that in mind. This is her output work and output power. So 241 watts, but they did want that in horsepower. So we're going to go ahead and exchange that from watts into horsepower. 1 horsepower is 746 watts. If you don't have that memorized, wow. No, you shouldn't have that memorized. It's up at the top of the gold equation sheet. Up in the corner there, it'll tell you 746 watts is 1 horsepower. Throw that in the calculator, see what you get. You get 0.32 horsepower. So about a third of a horsepower. As you'll find when we do our lab activity this chapter, you're going to figure out your own horsepower going up some stairs. So get ready for that.